Mr. Rainsberg here to go over the Chapter 9 practice test, and particularly I'm going to go over the multiple choice portion. In this video, if you look down at the length of the video, you may go, wow, that's long. But be aware that it's that length because in each problem, I'm not just telling you what the right answer is. I'm also telling you which ones are not the right answer and why, as well as how to eliminate choices. So every problem, I'm going through all the choices, and I'm also trying to teach you some strategies here. And because when it comes to the multiple choice test, it's not about choosing the right letter. It's also about finding which ones are not the right answer. You have to be able to analyze and figure out which choices cannot be the answer to sometimes help you find out which ones are the answer. But without further ado, let's start. An opinion poll asks a random sample of adults whether they favor banning ownership of handguns by private citizens. A commentator believes that more than half of all adults favor such a ban. The null and alternative hypotheses that you would use to test this claim are, well, I'm going to want to read all these. And what I'm going to do is I'm going to scan that list over there, and I'm going to see that there's probably a couple I can eliminate. And really, I can eliminate choices A and E right away. Because A is talking about using a sample proportion in the hypotheses. And hypotheses are stated with parameters, not with statistics. And then part E, your null is always based off of being equals to, that there is no change. And so if you look at E, the problem with E is your null hypothesis has an inequality symbol in it, which leaves me with choices B, C, and D. Now, those are all based off directions. So if I look in the prompt, maybe there's a key phrase that gives me a direction. In this case, it's the idea that he believes more than half of all adults favor such ban. So his is going to be P is greater than 0.50, which means the answer is B. Now, if I look at the next one, number 2 is a lot of reading, and you got to go through this. So you're thinking of conducting a one sample t-test about a population mean mu using a significance level of 0.05. You suspect the distribution of the population is not normal, and there may be a low moderate skewness to it. Which of the following statements is correct? So in this case, I actually have to read all of these statements here to figure out which one it is. So I'm going to start at the bottom when it says which of the following statements is correct. And I'll work to the top. So T procedures are robust. Well, I should probably finish reading that, but as a student, I may go, wow, I've heard Mr. McNichol say that before. I've heard Mr. Rainsberg say that before. So you know what? Let's put that one in the back burner and come to E a little bit later. If I read D, it says you can carry out the test only if the population standard deviation is known. Well, that's a concept right there. Because if I know the population standard deviation, I'm going to be using a Z test rather than a T test. So I can eliminate D right away. Because if I knew what sigma was, I would be doing a Z test, not a T test. T tests are used when you do not know your population standard deviation. C says you can safely carry out the test if there are no outliers regardless of the sample size. But then I'm also going to look up above. B says you can carry out the test if your sample size is large and there are no outliers. Do you see how B and C have a very similar phrasing to each other? So my mind's going there. A says you should not carry out the test because the population does not have a normal distribution. That might sound pretty nice. But what I'm going to do is I'm going to actually take a moment and think about what do I know about t-tests. And there's 3 cases when it comes to sample size. When n is greater than or equal to 30, we can use the central limit theorem to say t procedures are safe. If it's between 15 and 30, we can say it's safe to use them if there are no outliers and there's not a strong skewness to it. If it's less than 15, there better not be any outliers, there better not be any skewness in it at all, because your sample size is so small. So with these 3 cases in mind, maybe I can do something and eliminate more choices. So if I go back through, the next one I'm going to eliminate is I'm going to eliminate a couple of the trick ones. And the trick ones are A and E. And do you notice how I said B and C are worded very similar to each other, which makes me think maybe one of those is going to be the choices? A says you should not carry out the test because the population does not have a normal distribution. Well, it does say that in the prompt. But if you look at choice 1 here, it says you can use T procedures if your sample size is large enough. And so it is still possible to use T procedures. Or if your sample size is not large enough, hey, you know what? Does it not have a strong skewness and are there no outliers? So I can still use it even if the population distribution is not normal. Now, E, all the way at the bottom, says T procedures are robust. And man, that sounds good. But notice there are restrictions to how robust it is, based off sample size, based off the shape, and based off of outliers. So it's not perfectly robust. There are certain characteristics it has to hit. So B and C are my choices that I'm stuck on. Well, if I'm stuck on them and I see how they're worded so similar to each other, what I'm going to do is I'm going to look at what's the difference between them. So notice both of them say you can safely carry out the test and there are no outliers. So what didn't I highlight? Well, in part B it says if your sample size is large, and part C says regardless of sample size. Well, if I look at the list over here, sample size does matter when it comes to T procedures, especially when it comes to the idea that you were told that the shape was moderately skewed. So if it's moderately skewed, it will not qualify down here. And that means as long as I have a large enough sample size, well, look at that. If I have a large enough sample size, I should be able to apply the central limit theorem to say T procedures are safe. So there's the first two problems. All right, question 3. This one, looks like a two-way table there. It says to determine the reliability of experts who interpret lie detector tests in criminal investigations. A random sample of 280 such cases were studied, and here's the results. A suspect's true status are the columns, the examiner's decision are the rows. If the hypothesis, the null hypothesis is the suspect is innocent versus the alternative hypothesis, the suspect is guilty, then we can estimate the probability that experts who interpret the lie detector test will make a type 2 error as one of those. Well, that's pretty difficult there because I know we were told by Mr. Rainsberg and Mr. Nichols that type 2 error is just really that 1 minus beta for the power, and we can use that to figure out somehow beta, the probability of a type 2 error. What about a two-way table? Well, when I go to two-way tables, I go back to conditional probability. So I'm going to think of it like conditional probability. A type 2 error says the probability of failing to reject the null given that the null should have been rejected. And what that means is, if you look at the first part here in black, it's the probability of failing to reject the null given that the null is false. Well, let's put that in context. That's the probability of declaring someone innocent when they're truly guilty. Now, if I think of it like a two-way table, and I think of it like conditional probability, I should be able to highlight. And if I do that, I can see the guilty column is my total, and that's 140 people. Well, if I look at my list, A through E there, I can eliminate a few of those choices. I can eliminate A, B, and E because those do not have that 140 as the total in the bottom of it with conditional probability. So that takes care of the guilty part, the blue part. Now the purple part is declaring innocent. So if I highlight the innocent row, you'll see that there are 15 people there. So I get 15 out of 140, so the answer is C. However, take a look down there in the bottom. Choice D is really a trick. Do you notice how that 9 is not highlighted in the two-way table? That 9 out of 140, in this case, is going to be the probability of committing a type 1 error. So keep this in mind that some of your choices are tricks. So let's look at number 4. Number 4, significance test allows you to reject a null hypothesis, yay, in favor of the alternative at the 5% significance level. What can you say about a 1% significance level? Well, again, I don't have a picture. I'm probably going to end up drawing a picture here at some point, but I'm going to have to read through all these choices. I have to read every single one of them, so that takes time. You know what? I'm going to start again. Let's just say at the bottom. The answer can't be determined from the information given. You're tempted, aren't you? You're tempted just a little bit. It's the easy choice. You know what? Put it on hold. We'll come back to that one later. D says the alternative can be rejected at the 1% significance level. C says there is sufficient evidence to accept the null at 1% significance level. Well, I'm going to hold on a second. If I look at that C for a minute, and I'll come back to D as well, you never accept the null hypothesis. You never accept the null hypothesis. You always fail to reject the null. You never say the null is true. You fail to reject it. So I can, based off of that phrasing, accept the null, eliminate choice C. So certain words are really important to pay attention to. And if I look at another one that's very similar to that, it would have been D. Because D says the alternative is rejected. When you are doing your conclusions for hypothesis testing, you reject the null or you fail to reject the null. You do not reject or fail to reject the alternative. And so notice it is so similar. It's just one letter, the null hypothesis, H sub O versus H sub A. Those things are the ones you can't eliminate. But if you read too fast, your brain's going to think it said accept the alternative and reject the null for D. So you need to be careful with these readings. But what's nice is that eliminates two choices by being careful. So now I have there's insufficient evidence to reject the null at the 1% significance level, or the null can be rejected at the 1% significance level. Now, those two, if you think about it, those are opposites of each other, aren't they? You can reject the null, or there's insufficient evidence, you fail to reject the null. So A and B sound very like opposite choices. And I still have E that you were tempted by. So if I go through, I'm going to visualize this. I'm going to look at what it really shows. And so if I visualize it, here's what I have. I have alpha equals 0.05. That is my significance level. And that red area there is where I'm going to reject the null. The blue area there is my 0.01 significance level and where I reject the null in that case. Well, do you notice they don't completely overlap? There's overlapping in that tail part, but there's that little sliver in between them that they do not overlap on. So let's see what that means. If I look at the next page and I fill this in, the blue is the area where you reject at both the 0.05 and the 0.01, because that's that overlapping area. That little sliver to the side is where you would reject for 0.05, but you would fail to reject for 0.01. So you can see there's no overlapping here, which means there's an area where I could reject and an area where I would fail to reject, which makes choices A and B your really hard tricks, because they're true and they're false. There are areas where you would reject and there's areas where you would fail to reject on both cases. And so in that case, since the only two options there, A and B, there's a true statement, there's a false statement. The question always says, which of the following is the best? Well, we don't know which of those are the best because they can both be true or false. So in that case, your answer is E. But do not be tempted right away by it. Always sketch a graph first and visualize what you're looking at. So now we're going to move on to question 5. So number 5, a random sample of 100 likely voters in a small city produced 59 votes in favor of candidate A. The observed value of the test statistic for testing the null hypothesis H sub O of P equals 0.5 versus the alternative hypothesis H sub A, P is greater than 0.5 is. Well, again, I have to read all of these choices here. And one thing I notice right away is I'm dealing with a proportion. So if I read all the choices, the first thing I notice is that I can eliminate choice E right away, because T's are used for means when you do not know the population standard deviation. And then I'm going to look at the other choices. What's different between them? Well, one thing I noticed in the numerator is it's either 0.59 minus 0.5 or 0.5 minus 0.59. That order changes. So if I think about the formula, we know that for Z it's statistic minus parameter. So it should be 0.59 minus 0.50. That allows me to eliminate two more choices. So now the answer is either A or B. Well, what's the difference between those? And then that's in the denominator. And really, this is where your trick comes into play, is because choice A is based off of a confidence interval. Choice B is based off of a significance test. So we use p hat in our standard deviation when we don't know the population proportion. That's a confidence interval because we're trying to estimate it. But in a significance test, I do know the population proportion. I have a claim of what it is. So therefore, I can use that claim in the standard deviation formula. So choice A is a trick because that's based off of confidence intervals. Choice B is the right answer for this one. So question 6, a researcher claims to have found a drug that causes people to grow faster. I could have used that. The coach of the basketball team at Brandon University expressed interest but demands evidence. Good for him. Over 1,000 Brandon students volunteered to participate in an experiment to test this new drug. 50 of the volunteers are randomly selected. So volunteers were randomly selected. Their heights are measured. They are given the drug, and then 2 weeks later, they measure the heights again. The power of the test. Ooh, that word power is intimidating. The power of the test to detect an average increase in height of 1 inch could be increased. So we want to increase the power. By, well, again, there's this huge list, and I have to read, which means I had to figure out which ones are not the answer, along with which ones are the answer. So I'm going to go from the bottom to the top, or the top to the bottom, doesn't matter. Let's look at part A. Using only volunteers from the basketball team in experiment. Now that sounds eerily familiar, but here it just says using just volunteers. Notice the experiment itself had volunteers, but then those volunteers, there was random selection that occurred in that process. So without that randomness, we cannot perform inference. So I can eliminate choice A. And as I go through the rest of the list, there's actually another one I can eliminate. very, very fast is if I look at D, I am decreasing my sample size if I go down to 25 randomly selected ones instead of 50. And when you decrease your sample size, you know you increase your variability. Larger samples, as long as it's fitting into that 10% condition, are better than smaller samples. So now I have B, C, and E. And then when I get to this point, I'm going to quickly look at them and see what's similar, what's different. And when I see B and C, do you notice how really it has that 0.01 and that 0.05 trading locations? So my brain's thinking that B and C might be my answer, and I have yet to really read them. And I look at E, it says using a two-sided test instead of a one-sided test. And you may go, wait a minute, that sounds good, because in that case I have area on both sides where I would reject, so maybe I am increasing my power. But if I were to draw that picture out, notice when you create a two-sided test, that alpha level gets split between the two tails. So it's actually a smaller sliver in each tail on the outside compared to if it was just one tail, it would be bigger. So what happens is it's 0.025 in each tail. And that's really what this statement is telling you. And this is a misleading answer, or a tricky one, because the p-value is doubled on a two-tailed test, but the alpha level is cut in half. So you actually decrease the rejection area in each tail when you do a two-sided test. So be aware of that, which means B and C are my choices. So what am I going to do? How am I going to figure this out? Well, I'm going to again draw a picture, and I'm going to think about what it means for power. So let's go to this right side. Power is the ability to make a correct decision, which means rejecting the null when it should be rejected. So to increase your chances of rejecting the null, there's a couple things you can do. The first is you can increase the rejection area, which the rejection area is your alpha level. So in other words, you can increase your alpha level. And I can visualize it this way. If alpha sub 1 is the first rejection area and the blue one is the second rejection area, do you notice how there's more space to the right of the blue? Because I increase the amount of that rejection area. And so I can also increase my sample size, which by the way means I can eliminate D as well from that. So if I think about that, if I want to increase my rejection area, I would want to use a larger alpha value, which means my answer should be C. To increase your power, you can increase your sample size, or you can increase your alpha level. But also be aware, when you are increasing your alpha level, alpha is the probability of committing a type 1 error. So you're also increasing the ability of committing a type 1 error. So question 7, a 95% confidence interval for a population mean mu is calculated to be between 1.7 and 3.5. Assume the conditions for performing inference are met, random, normal, independent. What conclusions can we draw for a significance test that is two-tailed, H sub O, mu equals 2 versus H sub A, mu does not equal 2, so two-tailed at the alpha equals 0.05 significance level, based on the confidence interval that was given to us. So again, I have to read these choices and not just find out which one's the right answer, but which ones are not the right answers, which ones are the tricks. And so when I read these, notice A, B, and C, none. We cannot carry out the test without the original data. None. We cannot draw a conclusion at the 0.05 alpha level since this test is conducted at a 97.5% confidence interval. None. The confidence intervals in significance tests are unrelated procedures. I mean, look at that. None, none, none. Do you know what's interesting about those three choices, though? I can eliminate them right away. If I start with choice C, it says that confidence intervals in significance tests are not related to each other. They're unrelated procedures. And that's not true in this case, because a confidence interval is related to a two-tailed significance test. If you have a 95% confidence interval, you're trying to capture 95%, the outside tails are the significance tests, the 5%, that alpha equals 0.05. So 95% confidence interval relates to a two-sided significance test where alpha is 0.05. So I can eliminate that. I could also eliminate A. We cannot carry out the test without the original data. Well, we know all the conditions were met. That was told to us. We had the original confidence interval, 1.7 to 3.5, and we know there's a relationship between confidence intervals and significance tests. So I can eliminate A as well. And B, well, it's not related to a 97.5% confidence interval. Now, I'm thinking that one, there's thinking, hey, if I take that 0.05 and divide by 2, I get 0.025, and I would take 1 minus 0.025, I get 0.975. I'm trying to figure out how they figure out C as one of the choices, but it's wrong. So I'm related to D and E. Those are my two choices right there. I got to figure out which one it's going to be. So I'm going to continue and I'm going to analyze. I'm going to draw my confidence interval right there. And if I label my distribution and I label my confidence interval, I could see that I capture the population mean. The confidence interval captures the claimed population mean. So therefore, we fail to reject the null hypothesis. So my answer here is E. And notice when I eliminated, my two choices were D and E. One says you reject the null, and one says you fail to reject the null. You see how they're opposite decisions. One, if you choose one, you guarantee the other one's not going to happen. So I visualized it to see, did I capture the null hypothesis? So number 8, in a test of the null p equals 0.4 and the alternative p does not equal 0.4, again, something's telling me that's a two-sided test. I need to keep that in mind. A random sample of size 100 yields a test statistic of 1.28. The p-value of the test is approximately equal to, oh, that doesn't sound too bad. I have a test statistic and I massify the p-value. Awesome. This is going to be a pretty simple problem. Well, let's go through it. First off, I'm going to again remind you, it's two-tailed. Be aware it's two-tailed. Why does that help us? Because if we do two-tailed, remember, I have to double my p-value for this. That's going to cover both tails. So I would eliminate choice C. Not strongly in the beginning, but if I had choices, I would go there because C is a choice for students who might confuse p-value and alpha level, or they might say, hey, 0.05 is bigger than 0.04. I'm going to eliminate 0.05. I personally think that's one of the choices because someone might get alpha level confused with p-value. So if we continue on, I'm going to draw this out. And so I have a test statistic of 1.28. And so I went to my calculator and I did normal CDF because it's a p, which means I'm dealing with C's. And so I find this area to be 0.1003. Awesome. Do you know why that's awesome? It's because look at choice E. Choice E says 0.10. But there's a problem. That's a trick. Because based off my picture, if I think about just this picture, I did not heed my own warning about that caution. I did not realize that I should draw the second tail as well. So choice E is for those students who forget that it's a two-tailed test because they just go right to their calculator and they get 0.10. But you go, hey, well, Mr. Ainsberg, that's why I don't like the calculator. I use my table A for Z's. Well, good for you. Well, let's take a look at table A. And if I look at table A, notice I get 0.8997 there. Beautiful, because you know why that's beautiful? Look at choice A, 0.90. Do you think someone who sees that 0.8997 will choose that 0.90? So even table A is a trick. Because people who choose A, when they use table A, they forgot that table A gives you area to the left, which means they forgot to do the 1 minus. So in this problem, there is a trick for those who use their calculator, and there's a trick for those who use table A. So now it's either 0.2 or 0.4. Well, if it's two-tailed, and I know one of the tails is 0.1003, I just got to put the other 0.1003 there, and that's going to give me the 0.20. Choice D. I love this problem because for students who rely on table A, there's a trick for you. For students who rely on the calculator, there's a trick for you as well. So finding those tricks is a key concept. So let's move on to question 9. So question 9, a simple random sample of 100 postal employees found that the average time that they worked for the Postal Service was 7 years with a standard deviation of 2 years. Do these data provide convincing evidence that the mean time of employment, mu, has changed from the value 7.5 that was true 20 years ago? Now, I know the next sentence there goes over the hypotheses, but one, is there convincing evidence? That convincing evidence phrase tells you you're doing a significance test. Has it changed? Well, notice that's kind of vague. It's not saying, is it more, is it greater, or it's not saying, is it smaller, is it less? It's just saying, has it changed? And if it's not given a direction, and it's just like, is there a change? You don't care if it's more or less. You just care, is it different? So that's why in the next sentence, you can see your null hypothesis is that mu equals 7 hours. And your alternative is that mu does not equal 7 hours. It's going to be a two-tailed significance test. And we're asked, hey, what conclusion can we draw at the 5% significance level? Now, in the grand scheme, really, if I look at this paragraph, I can think of it like a state plan do conclude, because, I mean, it's asking me what I can conclude, so I have to really look at the whole test. I'm going to have to do the whole thing in a way. But do you really? Because I can read these choices and see, can I eliminate something? But before, I'm going to keep in mind some of the things that we already know. It is two-tailed, and my degrees of freedom is 99. Because I'm doing a t distribution, and so my sample size is 100. I know my degrees of freedom is 99. So I'm going to keep those things in mind. And when I read my choices here, let's go from bottom to top. because it does say what conclusion should you draw. So maybe I'm just going to start from the bottom and work up. We cannot draw a conclusion at the 5% significance level because, well, our sample size is too small. Wait a minute, our sample size was 100. And I know it's a t distribution. We want to do a t-test here. Remember the whole idea, if your sample size is greater than 30, you can apply the central limit theorem to use t procedures. So I can eliminate E right away. Our sample size is large enough to continue with t procedures. So then I got to continue on through. There is convincing evidence that the mean time working with the Postal Service is now 7 years. Well, hold on a second. What does that mean? There is convincing evidence that the mean time working with the Postal Service is now 7 years. Well, wait a minute. That's concluding sample proportion. You don't conclude your sample proportion. You don't conclude that the p-hat is the new population. Remember, you conclude you reject the null or you fail to reject the null. You don't conclude the sample proportion. Also, by the way, this is a one-tailed conclusion. That's the other thing about this one, is it's not stating the conclusion like it is a two-tailed test. So I know it's not D. Let me go to C. There is convincing evidence that the mean time working with the Postal Service is 7.5 years. Look at part B. There is not convincing evidence that the mean time working with the Postal Service has changed. Look at A. There is convincing evidence that the mean time working with the Postal Service has changed. A lot of these kind of look familiar. I mean, A and C has some of the same reading to them. B go through, but hold on a second. Let's go back to C. There is convincing evidence that the mean time working with the Postal Service is still 7.5 years. Was it 7.5 years? Isn't that our null hypothesis? So in C, aren't I really saying that I am, let me go down, I'm accepting the null? Hey, it's still 7.5 years. No, you never accept the null hypothesis. And so C is really accepting the null hypothesis in context. It doesn't say the phrase, accept the null. It says the phrase, accept the null in context. You're concluding that it is still 7.5 years. No, it's either it's not that you fail to reject or you reject the null. You never conclude the null in context. Part B, if I look at that one, choice B, sorry. If I go through and look at this one, I'm going to continue on. And what I'm going to do is I don't know the difference between A and B. There is convincing evidence that the mean work time has changed, and there is not convincing evidence between the mean work time has changed. I don't know which one it is. I have to do the work. But notice A and B are different conclusions. One is saying there is convincing evidence, which means you reject the null. One is saying there's not convincing evidence, so you fail to reject the null. And so what I'm going to do is I'm using my calculator. I went to t-test. I inputted all my information in there. Notice it's not equal to, I have my sample size, I have my standard deviation, and I can hit draw, and it gives me my p-value, which is very nice because it doubled it for me. Thank you, calculator. And I can also have it just spit out the data as well instead of drawing it. Now in this case, our p-value is 0.014 for both of them. That's less than the significance level of alpha equals 0.05. So we can reject the null and conclude the alternative. There is enough evidence to conclude the alternative. So my conclusion here is that I'm going to reject the null and I'm going to conclude the alternative, that the time has changed. And so in that case, my answer is A. So A is rejecting the null and concluding the A is rejecting the null and concluding the alternative in context. B is failing to reject the null and not concluding the alternative in context. Those are opposite decisions based off of your p-value. So A and B were the ones I would have been leaning towards being one of the choices, because one draws the conclusion one way, one draws the conclusion the other way. I did have to do this one, but I didn't do it by hand. I used my calculator because it was a lot faster for me, and that would have saved me some time. Last one is number 10. And so if I read number 10, are TV commercials louder than the surrounding programs? To find out, a researcher collected data on 50 randomly selected commercials in a given week. With the television's volume at a fixed setting, they measured the maximum loudness of each commercial and the maximum loudness in the first 30 seconds. A regular programming that followed. Assuming conditions for inference are met. So that means assuming random, normal, and dependent are met for this. The most appropriate method for answering the question of interest is. So hold on a second. I have to kind of think about this. One proportion z test, one proportion z interval, a paired t test, a paired t interval. All right, so I have proportions, and I have paired. Now, hold on a second. Proportions deal with categorical. I'm trying to measure the volume, aren't I? I'm dealing with quantitative here. So really, I can eliminate some of the things. One, I'm going to write down some of the information I know. I know my sample size is 50. I know I'm collecting from 2 samples. Loudness of each commercial and loudness in the first 30 seconds. And really what I'm going to do is I'm going to, same sample, I'm going to actually pair those together. So when I look at this, I'm going to eliminate A and B right away because I'm not even dealing with categorical. I'm dealing with quantitative. So look at that. I'm down to a 33.3% chance of guessing. I eliminate 2 answers. I'm good to go. And by the way, C and D both deal with the word paired. So that's awesome. Now I have to figure out, is it a paired t-test or is it a paired interval for t? Well, assuming which one works, if I look at this, assume conditions for inference are met. They want to determine, which one am I dealing with? Well, in this case, they said, is there sufficient evidence? When they say that phrase, is there sufficient evidence, then I know I'm dealing with a test. If it doesn't say that, it says try and estimate an interval, then I'm dealing with a confidence interval. Or try and estimate the values for it. I'm dealing with a confidence interval. In this case, I'm dealing with a paired t-test because I have that one sample and I'm measuring 2 different things and I want to compare the loudness with each other. Is one louder than the other? So kind of like a before and after, a new and old. And so this one is going to be a paired t-test. So hopefully you found this pretty helpful in the grand scheme of things that we did all the problems, 1 through 10. You didn't just find out what the answers were, you found out what the answers were not to help you figure out some multiple choice strategies on AP statistics tests.